last day. So today I think what we're going to do is we're going to start by finishing by proving an upper Gaussian bound estimate on the heat kernel. And then what we'll do with the time remaining is that we'll basically state everything that we should have done if we had had time. Just about basic estimates on heat kernel. So what else is true, and I'll just sort of make a list so you can kind of get a feel for what it is that's supposed to be true in this case, and then we'll kind of take it for granted if we have time and use it to actually prove something that actually is very interesting. Although it won't look very interesting to you, it is in fact very interesting. I'll kind of try to explain why it's very interesting. It's just a basic estimate on harmonic functions that was first proved by Cheeger and Kolding. Basically just the Hessian is in L2. Which sounds like a weak enough statement, but if you view it the right way, it turns out to be key to many, many things. So to prove the upper Gaussian bound on the heat kernel on spaces with lower Ricci bounds, so we want to start with two little lemmas, and these are really actually very nice lemmas that really hold an Ini-Riemannian manifold. They really have nothing to do with lower Ricci curvature. So the first of which is the following. So let's just say, take some complete space. Though in fact, it's possible you can get away with removing this if you just add boundary conditions. Guess maybe we can check this during the course of the proof. So take some complete space, and let's let C of xt, say, be at least a locally Lipschitz function. Which satisfies a certain differential inequality. So namely, such that ddt of Gauss plus 1/2 the gradient of Gauss squared. And this is supposed to be less than or equal to 0. Now, there are a couple of common examples of such things, by the way, on any smooth Riemannian manifold by taking certain functions of the distance function. Now, there's actually more than one. I mean, the reason we're listing this for an arbitrary function is that there's more than one nice choice of function here that will give us information. So it's better just to do this in generality. Then, if U sub t solves the heat equation, then J of t, which is defined to be the integral of U sub t squared, let's say of x, times e to the Gauss t of x, on our space is non-increasing in t. So, I mean, the key point of, well, a good number of estimates in this business and others are monotone quantities. So when we find monotone quantities, we always get new ways of estimating things. So this is somehow a nice point. So maybe what I'll mention even before I go through the proof is just two examples of how you use this. So I mean, the first thing is that you can let Ct of x be just, let's make sure I get my signs right, this is distance squared from some fixed point over 2t. So what this is basically saying is that if, for instance, your solution was initially compactly supported or something like that, so that you knew this integral at time 0 was some finite something, then the point is that you always have to have really nice Gaussian bounds on the thing. You could also, by the way, do this if you wanted to get some sort of better estimate. So that way it doesn't blow up at t equals 0. So that way it forces sort of Gaussian decay on solutions automatically is kind of what this is saying. This is pretty much on an arbitrary manifold, so this is actually a pretty nice statement. And the second application of this, which is actually going to be really important for the next sort of generic lemma we prove, is to let c(t) of x be, say, alpha times the distance function minus alpha squared over 2 times t. So alpha is just some positive something. So in both cases, you can check it satisfies this inequality, and that this is just because, I mean, the key point here is that the gradient of the distance function from a fixed point is identically 1. So if you just sort of use that and plug everything in, you'll see you've got the right inequality here. Okay, but let's prove this, which is not so bad. So the proof of our statement goes as follows. So what do? We just compute the rate of change of the silly thing. So d dt of j of t, this is just equal to what? I mean, we're going to get two components, right? We're going to get 2 u sub t dot plus k sub t dot times e to the k c. Right, so the first term just hit the u squared and left this thing alone. Second term hit this, oops. Gotta multiply this by u squared. That's better. Second term hit this guy and left the u squared alone, which just brought a c dot downstairs. Now there's basically just two things we know. We know this thing solves the heat equation. And we know that this thing here satisfies a certain inequality. So all we can really do at this stage is plug both these things in. So if we plug them both in, what do we get? Well, this guy, we just have an equality. Let's just write it out. We get that's equal to the integral of 2 u sub t, Laplacian of u sub t. And this are both non-negative, so we can just plug in our inequality here. Get this is minus less than or equal to minus 1/2 the gradient of c squared u squared e to the ct. Now what? So all that's really left to do that we can do is take this Laplacian and do an integration by parts. Move it over to the other side. Try to collect terms in some nice way. So if we move one of these gradients over, what do we get? Well, we're going to hit two terms here, right? Where we're going to hit, when we move, I mean, this is the divergence of the gradient here, right? This is divergence of gradient u. So when we move it over, we get a minus sign, and we have to hit the gradient of what's left over, which is this times this. So we get minus 2 times what? Times the gradient of u sub t. Gradient u sub t. So if we have it hit this guy first, then we get this times, well, the e to the c. And then if we have it hit this, we get plus u sub t gradient of ct gradient of u sub t. E to the ct. Oops. And plus our other term, of course, which is minus 1/2 the gradient of ct squared u sub t squared. And all of that gets multiplied by e to the ct. Rewriting this gives us what? It gives us, this is minus just the minus 2 times the gradient of u sub t squared. This here is just plus, how should we view this? Let's view this as u sub t gradient of ct gradient of ut. And this is minus 1/2 the gradient of ct squared u sub t squared times e to the ct. Okay, but what is this silly thing? So if we just write this out, this is precisely equal to the integral of minus a half times u Cassi u sub t Cassi t plus 2 times the gradient of u sub t squared, e to the Cassi t. But I mean, certainly that's less than or equal to 0, which is all we're trying to show. Right? So that this is not too much, right? So I mean, when you're trying to prove something like this, basically what happens, I mean, if you just start it with not knowing what your right condition was there, but you're trying to find some sort of differential inequality that you know should depend on just gradients or something, so you can use distance functions to bound things, you might start with something like this, do the silly computation, but you keep your u sub t, and at some stage you realize what u sub t needs to be, so you can give this thing a sign, and you just declare, okay, well, if it has that, now we have a sign. So roughly speaking, this is how you sort of guess stuff like this. But once you have it, it's quite useful. Okay, fine. So we have some nice little monotone quantity here, but who cares? What do we use it for? So what we're going to prove here is the following. We're going to prove, this is called Davies inequality. Let me go ahead and write it over there, because somehow with this big chalk things never really seem to take just half a board. So again, this is a very general point about Riemannian manifolds. So we just let M and G be some complete something or another. And let's take two measurable subsets. In practice, we're only going to really care about applying this when they're balls and what we're going to be using later. But so, I mean, they're very nice looking subsets, you know, compact support, open or closed or whatever you want. Doesn't really matter. But in general, this is true for measurable subsets, so let's just say it that way. Then we have the following estimate on the heat kernel of the Laplacian. Let's look at the heat kernel at time t, evaluated at xy. And let's integrate the whole thing over A cross B. Right, so the heat kernel at some time t, we can view this as a function of two variables, x and y, and sort of viewing A cross B as being a subset of M cross M. We're just integrating this thing at time t over A cross B. And we have that this is actually less than or equal to the volume of A, the square root of the volume of A, times the square root of the volume of B, times e to the minus the distance squared between A and B over 4t, where the distance between A and B is the geodesic distance. So that this just means the minimum of all distances between XA and YB, say, where XA is inside A and YB is inside B. So it's just the minimum distance between these two sets as sets. So, I mean, basically, up to an integral, we see that the heat kernel on any Riemannian manifold actually kind of looks like a Gaussian. Right? It's got sort of a nice little Gaussian decay thing going on. The only point is that this is somehow how you interpret your Gaussian or what you do with your Gaussian kind of depends on, you know, how the volumes of these sets are depending. But still, there's some very generic statement that says that in integral form we have something that sort of matches as a Gaussian for our heat kernel. So proof. Our goal, by the way, will be to basically just apply this to two balls around 2 points and use the Harnack inequality from last time to turn this integral estimate into a pointwise estimate. And then that's what's going to happen here in the case of lower Ricci. So how do you prove this? Well, let's do the following. So let's consider a certain solution of the heat flow. Let's let U sub t be the heat flow of the characteristic function of A. And so that this is the function on M, which is 1 whenever you're inside A and 0 otherwise. So, I mean, this is, say for the sake of argument, these are two, bounded compact sets. Just for the sake of argument, doesn't really matter, but just to be clean. And so all we're really saying is that, this is a perfectly nice L2 function, and we're flowing it by the heat flow, and this is our solution. So this is some nice smooth something for every T positive. Then this lets us rewrite the above integral, right? So this double integral can be rewritten then as, well, let's switch the order of integration. X of xy dy dx. And let's write this as being the integral over b of the following. This is just, view this as being the integral over all of m of rho sub t of x, y, times the characteristic function of a at y, dy dx. Okay. So integrating over the sets, over a set A is the same thing as integrating over the whole space, but multiplying it by the characteristic function, right? But this is a particularly nice way to view this because, from the definition of being a heat kernel, this thing is exactly just what you get by taking this function, flowing it by time t by the heat flow, and evaluating at x. So this is precisely equal to the integral over b of u sub t of x dx. Now we'll do some silly little estimate here. Let's just say, well, let's just use our Cauchy inequality to view this as being, right? So if you view this as being 1 times this thing, you can write this as being the square root of the integral of 1 squared over b, but this is just the volume of b, times the square root of the integral over b of u sub t squared of x dx. Go ahead and keep that top board just because we're about to use it. So let's just maybe not get rid of that so we can point to it. Okay. So what we need to do now is estimate that guy there. That is square root of u sub t squared. That's what we need to actually finish our argument. So let's just play with this formula for a little bit. So first off, we had these 2 examples of Cauchy we could use, one of which I just erased. I'll just rewrite it now. So, or actually, this is not quite one of the ones I just erased anyway. This is very, very similar, though. Let's let Cauchy tx be the following. Let's let it be alpha times the distance from x to a minus alpha squared over 2. Over 2t. So notice that, this thing here is still a perfectly nice Lipschitz function whose gradient is 1. Right? So, you can really apply this to any distance function. It doesn't have to be to a point. And you still have this formula. So this is a Cauchy, which satisfies the above. So what we really want to do is find out what happens when we plug that u sub t and that Cauchy sub t into this formula here and see it's non-decreasing. So let's break this up into a couple of points. So 1, if x is an element of B, just for the sake of argument, then what can we say about this guy here? Then Cauchy t of x is, well, it's the distance from x to a, but that's certainly bigger than or equal to alpha times the distance from b to a minus alpha squared over 2t. Point number 2. If x is an element of A, on the other hand, then cos 0 of x. Well, cos 0 of x, well, I mean, at time 0, this term goes away. So it's just the alpha times the distance from x to A, but this is 0. So what does that mean? That means that, well, let's do this on the next board. This means, on the one hand, that if we look at j of 0, then j of 0 is just equal to the integral of u sub 0 squared times e to the cos t. But this is just the characteristic function at A. You square it, you still get the characteristic function at A. So just this is equal to the integral over A of e to the cos t of x. But this thing is always equal to 0 at whenever x is inside A. So this thing is equal to 1. So the whole thing is just equal to the volume of A. So that's nice. J sub t, on the other hand, which, by the way, is less than or equal to this is somehow the point. Well, J sub t is equal to the integral over m of u sub t squared of x e to the cos t of x. Well, these are both non-negative, so we can at least say it's bigger than or equal to the integral over b of u sub t squared of x e to the cos t of x. But now if we're in b, we can sort of ditch this term and replace it with our estimate over here to simply say that this is bigger than or equal to the integral over b of u sub t squared times, well, this guy here, which is e to the alpha distance of AB minus alpha squared t. In other words, this guy here is less than or equal to that guy there, which we really want to solve for what this guy is, because that's where our formula left off. So if we just multiply both sides by this, and what do we get? We get that the integral of u squared over b, u sub t squared over b, is less than or equal to the volume of A times e to the minus alpha, distance from AB, minus alpha squared t. This was actually for any alpha positive. Let's go ahead and pick a convenient alpha. So if we let alpha be equal to the distance from AB over t, then t or 2t? I have t here. I kind of feel like we want 2t here. Let's find out. I think it's going to be a 2. So if we let it be a 2t, then that says that this is less than or equal to the volume of A times, what's that? Plus alpha squared t. Thank you. Yes. Plus e to the what? So this will become distance squared minus distance squared over 2t plus distance squared over 4t, which gives us minus distance squared over 4t squared. Yes, exactly. So this gives us, let's just write the silly thing out. Distance squared of AB over, what, 2t? This is plus distance squared of AB over 4t squared, but that's just 4t. There we go. Perfect. So that means the whole thing is just with the 4. Okay, but we're done, right? I mean, if we plug this into our formula before, this just tells us the integral over a over the integral of b of rho sub t of x, y. Well, we already knew it was less than or equal to the square root of b, volume of b, times the square root of this thing. And if we plug that in, we just get exactly volume of, maybe I did in fact want t. Let's find out. Square root of volume of a times e to the minus distance squared over 8t. Yeah, we don't want that. So if we did 2 here, I shouldn't have downed my notes. Plug that in. We get that just to be t. Plug this in. We get, there was a 2 over in this formula. That's what I was missing before. That's why I confused myself. Perfect. So then we end up getting a 2t after we cross it off. Or, yes, which gives us a 4t afterwards. Is that right? Or am I still missing something? Nah, that's right. Thank goodness. Okay, that's the correct factor. Okay, there you go. That's it. So we have a nice little integral estimate on the heat kernel of any nice smooth Riemannian manifold. So let's prove some corollaries of this. So let's do this in 2 steps. So the first corollary is just that I just want to use this, but I want to plug in a very specific a and b here. Right? So in particular, you have the integral of, so let's pick 2 balls of some radius. So let's say square root, so epsilon times the square root of t around x, and the ball of radius epsilon times the square root of t around y. So pictorially, what we're saying here is that we really, to get an estimate on this guy, x and y, right, what do we really want to do? What we really want to do is pick like a and b to be like Dirac deltas, right? We really want just to evaluate at these 2 points. Well, we're not going to do that. Those aren't, I mean, that's not really a set. That's a distribution. But we're just going to take small little balls around 2 points x, y. Right? So this is going to be sort of our localization phenomena. So we're just going to look at 2 small balls around these guys. And small means relative to t, hence the epsilon square root of t here. So that's the right normalization to make things work out. And what we get from this is just that this is less than or equal to, well, some constant depending on n and epsilon times the square root of the volume. We're doing this for an arbitrary space right now, not lower Ricci, so let's just keep it as what's written up there. The volume of the first ball times the volume of the second ball times our exponential. So far, there's absolutely no work involved in what we've done. We've just plugged in the formula. And the only work that we have to do here is check what the exponential is. So what's the distance between these 2 small balls? And the point is that this distance looks like e to the minus the distance. Sorry, let's put a 1 here and a 1 here to clarify that means these are fixed and we're integrating over these. The distance squared of our 2 fixed points over not quite 4, but 4 plus, say, some universal constant c times epsilon t. So the point here is that when we take these 2 small balls, what do we lose? Well, I mean, the distance between the ball of radius epsilon square root of t around x and the ball of radius epsilon square root of t of y, I mean, this is, let's just draw a picture. Actually, we can just do this proof by picture, I think. So we want to know what the distance between these 2 balls are, because everything else is exactly the same as the last theorem. So what are we doing? We're really looking at this here, and we're looking at this here. Epsilon square root of t, epsilon square root of t. So really, I mean, what do we lose? We lose at most that and that compared to the distance. So this thing here is bigger than or equal to. So we want bigger than or equal to because we want the sign to reverse when we go the other direction. Just the distance between x and y minus, what, 2 times this distance. So 2 square root of t epsilon. Okay. Now I'm just saying take this, plug it into that. You could find out exactly what c is. I think h or 4 will do, but I don't remember, so we're just going to call it c. So again, this is on an arbitrary Riemannian manifold. It doesn't really depend on anything. Note, by the way, the only thing you really want to pay attention to when you do this computation is that square root of t in front of the epsilon is really important. So it's saying that this is like, I'm going to be a little bit more exact, this is like e to the c epsilon times this. Sorry, there's a little correction factor in front. So the point is that you'll end up getting some error by squaring this term out, but that could be huge if there wasn't a square root of t in front of this, right? But that cancels the over t. That's over here, and you just get some small little error in front. So the square root of t is sort of the important factor there for balancing it out. Okay. So let's use this to do the important thing. So this is on any space. We want something better on a space with a lower Ricci bound. And in particular, since we never really wrote out the Harnack for a lower bound, I'm just going to say non-negative Ricci. But again, the same works. If you just have a lower bound, you'll add a plus kt or something term to it. The Shane-Yale Red Book does that very carefully, by the way. So if you want to see the precise formula for lower k in lectures in differential geometry. So let's take some space which satisfies, let's just say, non-negative Ricci curvature. Then for every epsilon bigger than 0, there exists some constant c of n epsilon bigger than 0, such that the following holds, such that rho of t of xy has the following pointwise upper bound. It's bounded from above by c of n epsilon times the volume of the ball of the radius square root of t around x, the minus 1/2, times the volume of the ball of the radius square root of t around y, to the minus 1/2, times e to the minus distance squared of xy over 4 plus epsilon t. So the point is that if we drop the epsilons here, right, and we pretend like we're in Euclidean space, then this is just like, so this is like just volume, or it doesn't matter what point we pick, so it's just like the volume of some ball, a radius square root of t, which is like t to the minus n over 2, which we're all used to. This ended up being just some power of pi in front. And we just get to drop the epsilon and get exactly what the heat kernel is. So this is saying up to epsilon, we actually have a pointwise bound that looks like a space with looks like Euclidean space. Okay, so proof. So the point is that we just have to go from there, our integral estimate, to a pointwise estimate. So how do we do that? So the idea is this. So let's do 2 points. Let's let, on the one hand, z be in the ball of radius epsilon times the square root of t. In fact, I'm going to throw in an extra 1 plus epsilon, and we'll see why, around x. Then what did our Harnack tell us? Our Harnack tells us, in fact, that rho of t of x of yz is less than or equal to, let's see, even go the other way. Let's say 1 plus epsilon times t is bigger than or equal to 1 over 1 epsilon over 1 plus epsilon. Oops, 1 over 1 plus epsilon to the n over 2 times e to the minus distance squared of zx over 4t epsilon times rho t of xy. So what am I saying here? I want to take 2 points, one of which is going to be exactly y, one of our sort of base points. The other which is going to be z, which is just sort of close to our other base point, but not necessarily exactly equal. And we want to see that the heat kernel at this sort of pair of points is basically the same, meaning bounded from below by the heat kernel at xt. And to do this exactly, you've got to make the time go up a little bit, but whatever, and you get some error term. And then you multiply by the original heat kernel. But now the point is that if we choose x and z to be in this sort of scale invariant ball here, right, and then what do we get? We just get this is bounded from below by some c of n times rho sub t of xy. So as long as your point is in this sort of scale invariant distance away from x, that means that the heat kernel is basically not changed by more than a factor when you move it around. So let's keep the moral here in mind, right? So we've got our point x, we've got our point y here. And we're basically saying, well, what we want to say is that if we look at the heat kernel at any 2 other points, x1 and y1, then the heat kernel between these 2 points is basically the same as the heat kernel between these 2 points. That's going to let us actually apply our integral estimate there and turn it into a pointwise estimate. Okay. The second point's exactly the same. So that is if we let z be an element of the ball, around y instead, then we get the estimate that rho sub t of x z is bounded from below by c of n rho sub t of xy. So it's the precise same computation as there. And combining these, we also have if, let's say, x1 is inside the ball of radius epsilon square root of 1 plus epsilon square root of t around x, and y1 is inside the ball of radius epsilon square root of 1 plus epsilon square root of t of y, and the heat kernel at x1, y1 is bounded from below. Shoot. There's supposed to be a 1 plus epsilon here. Got to up the time, right? That's where all these extra sort of factors are coming from, right? Is that we have to go up a little bit in time. Is bounded from below by c of n rho sub t of xy. Okay. So now I claim we're done. Why? Well, let's just apply this inequality here at t plus epsilon. Right, so what we know is, so by the last inequality, we know, just because it's a nice space, that the integral over the ball of radius, so this is at t plus epsilon, so that means epsilon square root of 1 plus epsilon square root of t, hence my choices of funky looking balls, are on x times the integral over the integral of epsilon square root of 1 plus epsilon square root of t around y of rho of 1 plus epsilon t of x1, y1. Well, if we apply this in there, this just gives us, it gives us the same formula, right, except with some extra factors of epsilon. So this is less than or equal to the, just put it down here, less than or equal to the square root of the volume of the first ball times the volume of the second ball times some exponential factor, which should just throw in some extra, your t should be replaced by 1 plus the square root of t, but if we make c a little bit bigger, it's the same thing. So we can still call this c epsilon, and e to the minus distance squared of xy over 4 plus slightly bigger c times epsilon t. But this guy here, we have a pointwise lower bound that says that this guy here is bounded from below up to some constant or something, times the heat kernel at time t of x and y, our center points. So this thing here is just bounded from below by, well, this becomes a constant then in the lower bound, but that means we get the volume of these two balls, right? So we get the volume of, I am so tired of writing this ball, epsilon square root of 1 plus epsilon square root of t of x times the volume of the ball of the radius epsilon square root of 1 plus epsilon square root of t times y times rho sub t of xy times the dimensional constant. Keep that there. So that times that times that times that. But this is certainly all we're trying to prove, right? Well, up to a volume doubling, sorry. So let's maybe do one more step. But that just implies, so keep our heat kernel here, take everything else to the other side, and what do we get? We just get that rho sub t of xy has the pointwise upper bound of, well, some ridiculous looking constant, c of n, times, maybe some e to the c epsilon, but if we take epsilon, say less than 1, we can just absorb that into this and not worry about it, times the volume of the ball of the radius, because that's a little bit bigger, right? So I could just call this 2 epsilon square root of t of x. And there's a minus 1/2 here. I'm tired of square roots. The volume of the ball of the radius, 2 epsilon square root of t of y to the minus 1/2 times our exponential factor, e to the minus distance squared of xy over 4 plus c epsilon t. And now, what's the only thing that's not left here? The point is that we didn't want the volume of the ball of radius 2 epsilon square root of t. We wanted the ball of the radius square root of t. But this is just volume ontodicity, right? That means that you can replace this with the volume of the ball of the bigger radius, but you just have to multiply by the ratio of those two volumes in Euclidean space, which is just some function of epsilon, because they both have a square root of t in there. So this here is just less than or equal to some c of n epsilon times the volume of the ball of the radius square root of t of x minus 1/2 times the volume of the ball of the radius square root of t of y to the minus 1/2 times our exponential factor. The minus distance squared of xy over 4 plus c epsilon t. C here, right, was some universal something. It's maybe like 16 at this point. So that just means take epsilon and replace it by epsilon over c, and you just replace this with epsilon. It doesn't matter. Take a little smaller. So that's it. We're done. We got our Gaussian upper bound. If you can repeat this argument 3 times in a row and not mess it up, you can feel confident you're starting to know what you're doing. Okay, well, technical headaches are over. So now that we've just done one case, a little bit of detail, let's just say, what else is left? So what else do we care about showing? I mean, to actually get applications from all of this, we want a little bit more information. So let's just sort of have a little theorem. So again, I'm stating this in the context where the reach is not negative, but there's a version of this where reach is bounded from below by minus k, and we just basically add a t term up here. So if the reach is bigger than or equal to 0, then the following estimates hold. So 1. First off, we have a lower bound. That's Gaussian. That may seem like a silly point, but this is extremely important in the applications. This is also bounded from below by c of n epsilon times the volume of the ball of the radius square root of t of x. And I'm just going to say to the minus 1 here. So instead of having volume of x and volume of y, I'll just have one of the volumes. Seems you should be able to have both, but the way I quickly worked it out to make sure it was right this morning, just had one, but whatever. Minus distance squared of xy still scales correctly, or minus epsilon t. So we've got the same sort of lower Gaussian bound on the heat kernel. And not only do we sort of have Gaussian bounds on the fundamental solution, the heat kernel itself, we have Gaussian bounds on its derivative. So we can have the same estimate from up here, but if we throw in a T inverse, then we can sorry, that's the minus 1/2 the way it's written, actually. So that's just the gradient, not the squared. We have a Gaussian bound on the gradient. And more than that, we actually have, in fact, we write it this way. We have a t to the 1/2 of Laplacian of rho sub t of xy has the same upper bound. So we have to lose another t 1/2. I just put it here so I wouldn't have to rewrite that silly thing all over again. And we also have that t to the 1/2 times the time derivative, which is just the same thing. It's the heat kernel of xy has the same upper bound. So we have pointwise bounds now on the heat kernel, on its gradient, on its Laplacian, on its time derivative. Basically, that's where it stops for pointwise bounds, though. If you wanted a pointwise upper bound for the second derivative, the Hessian, this is wrong. I mean, you can't get such things. This is, as far as pointwise bounds are concerned, as good as you get right here. Okay, so what's a silly sounding but turns out to be extraordinarily important corollary of this so again, I'll just say it in the non-negative Ricci case, but it's definitely true for just the lower Ricci bound, but you should restrict yourself to balls of radius 1 right now. I'm going to say something for any radius, but the key point is that when you go to lower bounds than the Ricci, if it's not 0, you can't do any radius, you can just do radius up to 1. For any radius, there exists some smooth function, phi sub r, from the manifold. So for any radius in any x, there exists some smooth function in R such that the following holds. So it's a smooth cutoff function with good properties is the point. Phi sub r is 1 on the ball of radius r around x. Phi sub r is identically 0 outside the ball of radius 2r around x. And if we look at the gradient of phi sub r, or the Laplacian of phi sub r, so I've just multiplied them by normalizing factors, and they're uniformly bounded, pointwise. So that is, we can get a smooth cutoff function whose gradient and Laplacian are uniformly bounded. Note, on any metric space, you can do the gradient. Just take some distance function or something and cut it off. Right? So this part here is not so much. This part here is tremendously useful information. Roughly speaking, how do you prove this? Well, I mean, it really is, actually, going to be built this way. You're going to take some smooth function from R to R, which is itself a cutoff function, and you're going to compose it with rho sub t, so view this as a function of y real quick, of xy. So the point is, since you have upper and lower bounds on this thing, you can be guaranteed that in the ball of radius r, this thing has some definite size for t very small. So as long as this thing is 1 on that region in R, then the composition is identically 1 in your space. And outside the ball of radius 2r, it's at least smaller than that for t really small. So you can just cut this thing off. So you just compose this with a cutoff function in R, and you get a cutoff function in your manifold. And all those bounds over there just imply the same bounds hold for this guy. That's rough, but this is quick at this point. We're just sort of seeing where this is going. This, by the way, this corollary was first really proved by Cheeger and Colding, not like this. They had an extremely different proof of this, actually. But they were the first ones to really write that down and observe it's useful. And let me tell you how it's useful, and then we'll call ourselves done. So the final theorem is going to be the following. So mg, again, let's say Ricci bigger than or equal to 0, but there's a version of this for a lower bound. And let, say, u be a harmonic function on the ball of radius 2 around some point for the sake of argument. Then the average on the ball of radius 1 of the Hessian of u squared is less than or equal to some dimensional constant times the inf over all real numbers r of the average on the ball of radius 2 of x of the gradient of u squared minus c. So this may seem like a rather strange statement, but there's two things being said here. If you have a harmonic function, if you just ignore the inf part for a second, let it be 0, for instance, then if you have a harmonic function with a gradient bound, then it has a Hessian bound. This is one statement. More important here is that, so remember what the key step in the splitting theorem was. At some point, we had a harmonic function, and we wanted to say the Hessian actually vanished, and we did that by saying, well, the gradient was identically 1. so that when we combine that with the Bachner formula, we got the Hessian had to vanish. This is like an effective version of that statement, right? Because if the gradient were some constant, or just close to a constant now in L2, then the Hessian has to be small. Right? So this is the key estimate to prove an effective version of this splitting theorem, this almost splitting theorem of theirs. And the proof of this is actually very simple with the cutoff function. So let's do that. What's the proof? So we just start with the Bachner formula. And we multiply both sides by with r equals 1 up there. We multiply both sides by a cutoff function and integrate. So it's the integral of phi times the Laplacian, the gradient of u squared, is, I'm going to say bigger than or equal to, because this is non-negative, I'll just drop it. Let's just say 2 times the integral of phi times the Hessian of u squared. Both these are over the whole manifold. Okay. But this guy here now, I mean, it's the Laplacian of this, so I could take this and add any constant I want in there. Right? Just for a Hessian bound, it doesn't matter, but when we're trying to show Hessian is small, this is very important. So we can just throw whatever constant we want in there. And now the key point is that we can take this Laplacian, this is some smooth function with compact support. We can do an integration by parts twice. And this just says that it's the Laplacian of phi times the gradient of u squared minus c is bigger than or equal to 2 times phi with the gradient Hessian of u squared. Now, this thing is 1 on the ball of radius 1. So we could just say this is bigger than or equal to 2 times the integral over the ball of radius 1 of x of the Hessian of u squared. This is now uniformly bounded. So this thing here is less than or equal to some dimensional constant times the integral of at least the absolute value of what's left on the ball of radius 2, because it has support on the ball of radius 2. But, I mean, that's it. That's the estimate. So once we've constructed this nice smooth cutoff function, we get from this Hessian estimates. And maybe my last word before I'm done is just to say that one should appreciate the 2 here. You can't do better than 2 on this Hessian. If you could do better than 2, there's a tremendous number of theorems one could prove about spaces with lower Ricci. So, I mean, in the end, you kind of see that limit spaces, we kind of saw that limit spaces were smoothed away from a set of codimension 2, right? We saw the singular set in the non-collapse setting had codimension 2. It's the same 2, really. It's not so clear right now, but it is really the same 2. If you could push this to 2 plus epsilon, you could actually push that singular set back another dimension, right? And actually, if you have bounded Ricci, you can actually push this up to everything less than 4. But, I mean, under lower Ricci, that's as good as you can do. Okay, that's it. I'm done.